So for this hour, I would like to start a little bit on the new chapter, which is chapter 6. Okay? Even though we so chapter 6 in the textbook mainly focused on the introduction of MOSFET. Okay? Even though we spent like four weeks on bipolar junction transistors, and when I was taking device or circuit analysis courses maybe 20 years ago, 25 years ago, most of the textbooks focus on, a lot of the, especially analog circuit textbooks, focus on bipolar junction transistor circuits a lot. The main focus, the key focus. And when I was taking courses in graduate school, if you talk about Gray and Myers, those classic textbooks, they focus a lot on bipolar junction transistors because that's the mainstream solution. But nowadays, most of the circuit, because of the success of what we call CMOS technology. I don't know if anyone knows what CMOS stands for. Does anyone know? You can look it up on the web. But you see this a lot because this is the main key technology for a semiconductor industry. So what is CMOS? Does anyone know? Give it a name. MOS, everyone know, right? What is MOS? Metal oxide semiconductor, right? So MOS stands for, it's described the structure of the device. And this FET describes the operation principle. This gives you operation principle. So the naming, actually, operation principle. Right? MOS is the structure, the main structure, metal oxide semiconductor, that's described the structure of the device. And FET then defines the, so let me say, what is the structure is metal. So if you think about it, MOS stands for metal oxide semiconductor. Not wide enough. So there's actually, if you look at the naming of the device, it actually consists of two parts, the structure and operation principle. So FET stands for, what does FET stand for? Field effect. So FE stands for field effect. The last word, of course, is transistor. So I should say FE is the operation part. It's probably better just the FE. The last word is just transistor. So FE describes how this transistor operates is by field effect. Field simply means electric field. It's magnetic. It's not magnetic. It's electric field. Okay. So does anyone find out what? As I said, the reason why MOSFET technology becoming most prevailing, even in analog circuit regime, the main reason is because CMOS technology become very powerful. And does anyone know what C stands for? Complementary, correct. So C is complementary. So the main operation of complementary MOSFET technology is because it has P channel combined P channel and N channel. And these two channels, the word complement means that they complement each other, meaning that one is on, one is off. So it's like a seesaw. So it toggles on and off each other, from each other. Therefore, this is the core for logic circuits. So nowadays, I should say almost 100% of the largest circuit is based on CMOS technology. So because it's digital circuits is very, very powerful, a larger circuit, or I should say digital circuits, it's become much more powerful. Therefore, its peripheral, its analog components also being constructed with the same type of transistor, even though it's not that ideal for an analog operation. If you think about the characteristic, bipolar junction transistors actually have certain advantage in terms of delivering high gain and high driving current if you want to deal with analog signals. But because of you want to be compatible to this very, very strong monster of CMOS technology, therefore, MOSFET technology expanded into digital domain nowadays. So you see mostly all of them, all of the circuits are made by CMOS technology much more than just simply having bipolar. So bipolar is very, very weak now. Bipolar technology now is limited to mostly for power devices where you want to have very large amount of current to drive motors or other high driving current, high current driving circuits. Okay, so once we have this overview, let's look at what we're going to mostly address in this part. Of course, we're going to talk about the basic transistor structure, how it looks like, how it functions, its basic operation principle. So more intuitively as to understanding how this device operates. And of course, when an established IV characteristic, how does one characterize a device? You can measure it and model it. IV characteristic, and then of course, you want to have a current model, current voltage, I should say. I'm just going to write that. IV model. Current as a function of drain current as a function of gate voltage model. And of course, we're going to generate small signal equivalent model as well. It will be very similar to bipolar junction transistor in terms of small signal modeling, because whatever transistor needs to project or provide is very similar for both transistors, because transistors is to deliver a certain type of function. When you linearize it, it will look very similar. Okay, so let's first look at device structures and circuit symbols. So typically, when you look at a device, what we typically do is to look at in a different direction. So if I'm looking in from, there's two views. One is, I just use a. So there's something called a cross-sectional view. So it's when you cut it through a wafer. So you start at this is silicon, let's say this is silicon. The silicon interface. So I have silicon. Typically, you start with a P-type substrate. This is for cross-sectional. This is for a we start with looking at the N-channel device. Okay. One of the key functionality of a switch is that it has to be turned off and on. So you have to have a switch which control the off and on of the circuit. So this is the same thing. You want to make sure that it's supposed to be initially off, and then with the control of your third terminal, it turns on. So if you look at the bottom structure of the device, it will be something more like this. So for the silicon part, I'm actually constructing a device which is not connecting at the beginning. So I'm forming a N+ version under the silicon P-type substrate. So this is P, and you construct two connecting terminal with N+. And then this is being, I should use a different color. Change the color. So I'm starting with the substrate, and this is N+. So for this, I'm connecting to a metal. So this is the metal contact to the two most important terminals, which one is called the source, the other is called the drain. So I'm going to explain that a little bit. And then I'm going to build my MOS structure between these two terminals. So I'm going to have a structure like this. This will be metal, another metal, and this will be my oxide. So this layer is metal. So I'm constructing my MOS. Have a good enough color. So I'm constructing the MOS right here. So you have the MOS structure to induce a channel, and the channel is being connected out through these two terminals. And we control this field effect by terminal gate. So if you actually look at this device, it's essentially a 4-terminal device because your substrate is typically biased at a certain point. So my substrate also needs something to pick up. I need to generate a pickup. This is the substrate pickup. This is connected to a metal again. So this is referred to as the substrate pickup. So meaning that allow us to give voltage to the substrate. So essentially it's a 4-terminal device. It has, let me write it down, it has the gate mainly for creating field effect. To induce field effect, I should say. And I have the pickup to connect to the channel. So I have source. S stands for source. D stands for drain. Sorry. So source and drain, the main purpose of source and drain is to connect to channel. So let me write it down more. So through field effect is the main purpose of the gate is through field effect to create channel. So the main purpose of having a gate is to induce a channel. And the source and drain structure is mainly to connect to the channel. And then I have B stands for body, is to provide bias substrate. Potential. Typically, we don't, because body is typically shared by a lot of transistors, therefore the body is typically common. Common meaning shared by all transistors in the circuit. I should say all N channel or P channel, depending on the type. So if you have multiple transistor, N channel transistor, they share the same body. They're being made in the same body. So I can have multiple transistors made and in the same body. So it will then have a shared body connection. Okay? So we can also do the p-channel counterpart. Let me do it in the top. So for p-channel, if I'm drawing the cross-sectional view, typically, if you start with one type of substrate, if you want to make a p-channel, you need to build something called a well. So I'm starting with a p substrate. In order to invert the type, I need to make my the basis for building p-channel a n-type. Therefore, to do that on the same substrate, we typically create something called the n-well. N-well simply means that you counterdope, so that under this region, it will be an n-type region. And then I'm making my key structure, which is the connection, P plus. And then I will also have my N plus pickup. So then the structure on top is the same. I would then have my metal oxide structure, and then connection. This is to the gate, source, drain, and body. So the blue stands for metal contact. So for a p-channel device, this is for a p-channel device. The main difference is that you need to invert your substrate into an n-well in order to build P plus for connection. And your channel, whatever channel is being formed here, is we're going to mention that a little bit. Whatever channel we're forming to bridge these holes, bridge source and drains are constructs of holes. So your channels are mainly bridging by holes. In our previous case, this will actually be bridged by electrons. This is just to show when it's connecting, the channel is mainly composed of electrons bridging the two n regions. Okay? So this is the basic structure if you're looking at the cross-sectional view of a transistor. So how does one represent this in a circuit schematic? So circuit symbol, for circuit symbol, If you look at the circuit symbol, will look something like this. First of all, I want to highlight one of the things that if you look at this device, it's a pure symmetric device. Therefore, there's no difference between source and drain. I could assign this as source or assign this as drain. There's no particular reason why this terminal is source or drain, meaning that it's interchangeable. So let me highlight this first. The MOSFET devices are symmetric meaning that the source and drain are interchangeable. Especially when you're trying to do something called a pass gate. If you're passing it, this side can be sourced at one time, this side can be sourced at another time. But in most cases, source drain are defined by the biasing condition of your circuit. So it doesn't really matter which side you assign which, depending on when you apply your bias and where the current is flowing. So circuit symbol for N channel. For N channel device will look something more like this. There will be an arrow here to note where you pick this particular M+ as the source terminal. Okay? So there will be 4 terminals, as I said, there's a body. And then there's a gate, source, and drain. So you can see that at the symbol of the circuit is already implying that we're having a capacitor. It's like a parallel capacitance. So you're actually having a capacitor structure. If you look at metal oxide semiconductor, if you consider the semiconductor as an electrode, then you have a parallel plate capacitance. So you actually imply that there's a capacitance between the gate and the channel. So through this capacitance, I'm inducing a charge, then allowing the channel to be formed. So in this case, the arrow simply refers the direction of the current. Therefore, we know that because N channel, the channels are formed by electrons, therefore the electrons flowing from source to drain. So carriers are always flowing from source. There's a reason why we named this to drain. Everyone know what drain is. Drain is where you drain the water, right? So your carrier coming out from source, drain out by drain terminal. So this is for N channel. We can do this for P channel as well. Let me use a different color. So for P channel device, if you're doing analog circuit, typically you want to highlight the direction of the current flow. So this type of symbol is very common if you're doing analog circuit analysis. So this is the direction of the current. So you also have source, drain, gate. And then we have a body connection. So this is a typical circuit symbol. Let me do it to the top. I will explain why, because most of the body connection, there's a certain setting for body connection. So this is more for P channel device. This is the P channel. So we know that for P channel, because it's P channel, meaning that the carriers are holes. So I have holes in the channel going from source to drain again. So no matter is electrons or holes, both are flowing from source to drain. Okay? And the arrow simply referred to as the current direction. So whole current direction is the same as current direction, therefore, it's from source to drain. So this is mostly for the type of arrow indicator for MOS and PMOS are typically used for analog circuits. If you're analyzing digital circuits, for digital circuits, you will see symbols, a different type of symbols for if you're doing digital. N channel, P channel. You're more toward the logic concept of adding this. This is more to indicate you're having a P-channel device. Okay, so this would then, because in digital circuits, sometimes there's no assigned source or drain. So source or drain are interchangeable, so signal current arrow is meaningless. Therefore, to indicate P-channel or N-channel, this is how it's being labeled. Okay? So we're going to focus mostly, because we're not talking about digital circuits, but we're mostly going to use this type of notations in our follow-up analysis on analog circuit, MOS analog circuits. Okay? So another thing I want to mention is that because this is the main conduction mechanism of a MOS transistor is through whether there's a buildup of channel. So therefore, you wanted your current, your main control is at the surface. This is called the silicon surface. So what we want is mainly having the current flowing through the surface. We want to block anything under the surface, because at the surface or at the interface is the one that is being controlled. So what we want to do is to inhibit. So one of the key design in order for the drain current to be mainly controlled by the channel current is to inhibit other component, other leakage component. Because if you ignore the MOS structure, if you look at the bottom, it's an PNP. The top is an NPN. Therefore, there's a parasitic, we call it parasitic BJT, underneath this device. You want to disable that. You want to disable this parasitic BJT to make sure that your MOSFET functions being shown. You want to make sure that you see the channel effect rather than the underneath current. If you operate as a BJT, then there's an underneath current. So to inhibit we should say the BJT effect. You want to turn it off. You want to turn off. You make sure that junctions or PN junctions are always in reverse. We don't want any junction to be turned on, otherwise it will interfere with the control current, which is being built by the surface channel. So how does one do that? In an N-channel device, how does we achieve that? So in N-channel device, we want to make sure that our body is connected to BSS, the most negative voltage of the circuit. So make sure that potential of the P substrate is at the most negative. Therefore, whatever voltage is being applied on the source and drain, it will always be reverse bias PN junction. The second thing is that for P channel, it's the opposite. So we will have my body connected to VDD, which is the most positive potential. Potential in your circuit system. So by default, if you're not doing something exceptional, by default, this is connected to, your body is connected to VDD. And this body is connected to VSS. I should say minus VSS, just to show that it's the most negative potential. Whether it's 0 or most negative, you have minus 3 volt, you apply to the most negative. To ensure, this is to ensure that your PN junctions is always in reverse. So it's not to interfere this bridging effect, which is the gate control conduction between the source and drain. Okay? And the other thing I don't know if I want to highlight. I don't think we have time to go into the operation principles, but the other thing I want to highlight is that I have N plus and P plus as referred as heavily doped. The reason why we're using N plus and P plus for source drain is, first of all, you want to create the N plus is just to make sure that it will be connected to electron. It has a lot of electrons, so it's the same type. The other thing is, of course, the plus is to reduce, we call the series resistance. So series resistance is mainly the connecting resistance. You want to make sure that the resistance can be as low as possible. So typically it's making, we call the N plus version, to ensure that it's effective resistance coming. If you consider this, there's a parasitic resistance. So these are series resistance, RSRDs. So the reason why we're using plus is to make sure that the effective resistance is much smaller. And lastly, if I have a little time, so if you look at the structure when you cut it through the channel surface, perpendicular to the channel surface, this is how it looks like. But what if you want to look at as a bird's eye view, looking from the top? So let me give you an example as to what you need to draw. We call the layout or the top view of the device. If you're looking over the top, this type of device will look something like this. Typically what happens is that if I have a blank page of silicon substrate, let me just draw a very big one. So let's say if I have I start with a P substrate, everything is P substrate. So I need to define whether I want to put my NMOS and PMOS. So therefore, you need to define a region for, where's my wheel? Okay. So it's yellow. So I have to define a region for N well. So within this region, it's to create PMOS transistors. And then once this is being defined, one of the key things I want to mention is that you would then have, there's multiple transistors, so each transistor is being isolated by we call the oxide. There's another isolation between transistors, so typically at the edge, there's isolation. So there's isolations at the edge. So you want to make sure that you open up to the surface with a window. So this is called the active area. I'm going to explain that AA stands for. Okay? So the other part where there's no, it's not open by active area, is covered by isolation. So the rest, the surface is being covered, aside from the green part, the dashed line part, even with underneath envelope and P-sub, it's all isolation. So you want to make sure that your transistor is isolated from another transistor. And then we typically would then have my gate. So I would define a gate, something like this. This is also another, this is for PMOS gate. So this is gate. So you define the gate. And then I will define my source and drain. So for this is the N channel, so this is N plus. The whole region is defined by N plus, and then I have my P plus. So this will be P plus. So there will be an N-channel device, there will be P-channel device. This is how it's being made. And in this type of structure, we're going to use two of the key parameters. If you're looking at this device, there's two dimensions which is critical to the transistor. One is the distance between the N plus. The distance between the N plus is called channel length. The distance defined active area is called width. It's a channel width. Because it's the surface device, so the device characteristic is defined by two main characteristics. One is called W. Let me write down W. It's called a channel width. L is called channel length. And if I'm trying to draw the cut line for this, the cut line is through here. This is the BB cut line for getting the cross-sectional view, correspond to this, right? And then for CC, because I already used CC prom. So this is BB prom. This is the CC prom. So this is the top view of the device. And when you cut it in, you see this cross-sectional view, corresponding cross-sectional for N channel and P channel. Okay? Okay, so I think our time is up, so I'm going to stop right here. And we're going to come back on Thursday and dig into how does the device operate, different operation regions, how does one control. The main thing is how does one induce the channel, because we know that it's mainly being constructed by building up this channel. So how does one induce a channel through electric field effect? So it's not direct contact. There's no direct current flow. It's an induced force. 所以我常常说这个 MOSFET 就是隔山打牛，中间有隔一个东西。So this is very powerful against bipolar junction transistor because if you look at in terms of circuit perspective, there's no DC current flow. Therefore, it has infinite input resistance. That's how we get ideal voltage buffer. You can actually get more ideal voltage buffer because you have no direct current flow. It's a induced charge. So we're going to talk about that a little bit more. And that is why it's become very powerful to deliver what we call the CMOS technology because it does not, it has, if you consider current gain, it will have infinite current gain because there's no, your CP value is infinite. It's not essentially infinite if you're operating in AC mode, but in terms of DC, there's essentially no current flow because of the insulation, oxide insulation, MOS structure. So it's very powerful in terms of delivering low power complementary operation. That is why it's become very popular. So the basic plan for today, and at the end of today's class, I will give some hints as to the midterm exam questions because Professor Wang just gave me a copy. So I'm just going to go through what is actually included in the exam. Make sure you stay till around 12 so you get all the hints. Okay, so what we're going to do today is hopefully wrapping up chapter 6 if possible. But what we're going to do today is continue our discussion on MOSFETs. So we're going to start with basically operation principle of the device and also the most important thing when one discuss based on this, I should say, device physics, start bridging the device physics to the circuit, you basically need models. So we're going to do some simple derivation as to find out what is the main, in a bipolar junction transistor, the main current that we're concerned about is collector current. And in this case, it's drain current. In MOSFET, it's drain current. A better, actually, a more simple structure than BJT is because source current, drain currents, in most cases, is equal. So that anytime you talk about drain current, it should be identical to source current. And then we're going to talk about device models, both large and small signal models. So before we actually talk about operation principle, I wanted to spend a little time still talk about cross-sectional area, more precise or modern cross-sectional area. I should say it depends on what type of technology or what generation of technology you're using. You'll see different things when you cut into the transistors. So I'm just going to tell you this is probably something more submicron technology type of cross-section you will see. If you actually get a CMOS device. So let's say if you cut it into a CMOS circuit, so what you would expect in terms of, okay, let me. So for a CMOS circuit, you basically have two transistors, so we can also highlight N and P. CMOS simply means I have both N channel and P channel devices. Okay? So how does one construct both N and P channel devices on a single type of substrate? The key important thing is that if I want to construct an N-channel device, I want to have my substrate as P. It's an inverting type of operation. If you have a P-channel device, you want your substrate to be N. Therefore, you need to have different type of material, semiconductor material, on the same substrate. The way of doing this is to generate something called a well. So the generation of well is the same as the idea that we discussed last in previous lectures is the counter doping. So you start with a lightly doped P channel, P substrate, And then for the parts, you want to generate a p-channel device. We define we call the N well. Okay? And then if I want to control the doping concentration where the transistor is being placed, more precisely, the more modern, I should say, ways of making CMOS technology is that it creates two types of wells. So it will then create something called a P well. So because this is P, so this is shorted to the substrate. So this is the same type. This is the reverse type, different type. You could do that to make sure that you have better control as to doping concentration. So typically, this might start at a 10 to the 15th. This would then raise to maybe 10 to the 16th, at the level 10 to the 16th, for example. Okay? And then in most cases, because my transistors are highly packed, therefore, if you simply leave your PMPs, with a space, they wouldn't touch each other because junction itself is reverse bias. But if you want to pack your transistor very tightly, you want to make a more, I should say, a wall between the transistors so that the isolation distance between you and me can be closer. For example, if I'm putting on, let's say, if there's a law of isolation of 1.5 meters to make sure that there's no transmission of viruses, it's 1.5 meter with air. But if I add a shield, for example, if I add a glass, a piece of glass, then I could probably stand closer to this person without transmitting viruses. So this is the same idea. I want to make sure that my transistors can be highly packed. So what color do I have? So what can be done is you typically, between transistors, for example, I have N and Ps, and then I could insert something called the isolation. I'm just going to leave it as an isolation. So typically for isolation materials are silicon dioxide. And basically silicon dioxide are a good insulator. So these are insulators. So you insert insulator, a thin glass. So these are isolation structures. So these are typically placed to isolate transistors and also isolate different type of implants, and especially close to the surface. So it may be, these are not very deep. Slightly higher than your well level. And then what is typically done is that I want to do my transistors. So I do the isolations. And maybe internally there might be some isolations here. I just want to show some isolation. This is just to isolate the implants on top, the pickups. And then we're going to make our transistors. So when you make the transistors, we need a metal oxide structure on top. So there's another oxide here. And then there's a metal gate. So this is the metal gate. For PMOS, you also have a oxide. And then we'll have a metal gate. Okay, so these are still oxides. I'm just going to use SiO2. And then I'm going to make my source and drain. So for N-type, what color do I have? So for N-type, this is the N plus. N plus. Remember, you're creating NPN so that it will not conduct at the beginning without the channel. So you want to make sure that happens. For P-types, we have P plus, P plus. And then for pickups, you want to do the same type. So this will be P plus pickup. I'm sorry, the color. And this will be an N plus pickup. So these isolation will allow you to have these different types placed close together with a small isolation in between. If you don't place that, then you need to place them further apart in order to make sure that they are terminally and individually biased without any bridging of potential. Okay? So then the last part is that you're making contact to all these terminals. As I said, this is an N-channel device, therefore, I have 4 terminals: gate, source, drain, body. And for a P-channel device, we have source, drain, body. Okay? So these terminals are connected through metal again. So this might be identified as the source. This is the drain. This is the gate. And then I have a body contact right here. That's for the N-channel device. For P, let me use it. There'll be still metal contacts. Metal wires connected to these structures, and then I have also gate, source, drain. Okay? So that's a typical CMOS technology if you look at the cross-section. This is typically referred to as the twin well process. Twin well meaning that I'm doing 2 types of well. If you're skipping one, it could be single well, or this is twin well, and you can also do triple well. So this is like in between. Okay, good. So once you get a better sense as to how your device or circuit architecture look like, we're going to go into the basic operation, basic principle of a MOSFET device. So one of the operation, there's actually 2 things, I should say. As I highlighted in the naming of this device, first of all, it's a MOS structure. And the MOS structure is to induce the basic idea and more intuitive discussion. Channel charge. Or I should say channel carrier. To induce channel carriers, whether it's electrons or holes, the main purpose of having a MOS structure is to construct channel carriers. So we need to separate into 2 things. One is how does one induce the channel, and then afterwards, how does this carrier flow through the channel? So there's 2 parts. Once you have to induce channel, these charges are called inversion charges. Typically, we highlight it as Q inversion. Let's first limit our discussion on N-channel device. So for N-channel, the inversion charge mainly consists of electrons. This is for N-channel. So first of all, we want to induce charge. The next thing is that you want to make it flow. So the second part is once the charge being induced, you need to apply a field, electric field, along let's not move that. Apply an electric field so that these carriers can move. So once we apply electric field, I'm going to label it E, parallel. I'm going to talk about Y. We'll apply a parallel field so that it will move, so that there's a drift. force to induce a drain current. So the basic idea is, once again, you induce the channel, the formation of the channel, and then once these carriers are there, you need to push them, allow it to flow from source to drain. So one of the key important things is that it's a drift-dominated current. The current itself depending on drift component rather than diffusion. So you have simple one carrier. The only concern about is there's only one carrier. So if you ever do sort of device simulation study, this is called a one carrier problem. The reason why is that it's much easier without, if you're thinking about bipolar junction transistors, you always have to consider electrons and holes happens all together anytime you form-bias a p-n junction. In this case, there's only one carrier which is dominating your current flow in the system. So it's a much easier problem if you're doing simulation type of solutions. Okay? So, let's think about the first part. So how does the structure induce carrier? The idea, of course, we don't have time to go into detail as to the operation of an MOS capacitor. Typically, we call it the MOS structure. But I'm just going to give you a simple analogy as to how this happens. So basically, you think of your structure as a MOS. Okay, so there's a metal on top. And there's a, remember this is a P-type semiconductor. P-type silicon underneath. And then I have a piece of glass in between. So the oxide is typically silicon dioxide. You can think of it as a piece of glass. It's a silicon dioxide, it's an insulator. So the oxide referred to as an insulator. In silicon-based technology, it's typically SiO2. I have a silicon insulator in between metal and semiconductor. So the way to look at this is to view it very similar to, if this is a metal, we're assuming that the silicon is more like a conductor. So it's a conductor, oxide conductor. So it looks like a parallel plate capacitance. So you can assume that it looks like a parallel plate capacitance. So you can assume that it looks very much like a parallel plate capacitance. If you have a parallel plate capacitance, what happens is that if I'm applying voltage on the gate, so this is a gate, and the underneath is the body. Between the gate and body, what happens is that if I'm applying a positive voltage, there will be positive charge on top and positive. I say positive charge on top. It doesn't matter what type negative charge in the bottom. Okay?